Please catch it. Please catch it. Oh, hey. It's Mr. French, your AP Stats teacher. I'm just here playing some baseball. Let's go ahead and get started and think about some AP Stats. Hey, welcome to our first AP Statistics video. We're gonna go over the solutions to the questions from last week's Desmos quiz. We're just gonna jump right into it. We're gonna go over question 2 from 2019, and I believe question 3 from 2019, and then question 6 from 2019. So if you're looking for question 6s, this is the place to be. Take a look, jump ahead in the video if you would like to. We're going to start things off with question 2. Researchers are investigating the effectiveness of using a fungus to control the spread of an insect that destroys trees. The researchers will create 4 different concentrations of fungus mixtures: 0 milliliters per liter, 1.25 milliliters per liter, 2.5 milliliters per liter, 3.75 milliliters per liter. An equal number of the insects will be placed into 20 individual containers. The group of insects in each container will be sprayed with one of the 4 mixtures, and the researchers will record the number of insects that are still alive in each container 1 week after spraying. Question A, identify the treatments, experimental units, and response variable of the experiment. Okay, so by looking at your responses on your Desmos, I feel like we essentially got treatments correct. So the treatments in this case are the thing that we are imposing upon the units. So the treatments are the sprays with 4 different concentrations of the fungus. We pretty much did a great job there. Part B, the units. So this one I noticed a lot of misconceptions. Turns out the units are not, hi Ramsey, the units are not the insects. The units are the smallest thing in your experiment that the treatment is being imposed upon. So we know that the treatments are imposed upon the 20 containers. If we were to say that the units were the insects, we're putting a bunch of insects in the containers. We do not know for certain if these insects are going to react the same to each of the 4 concentrations, right? Like the ones at the top could get it sooner than the ones below. There's no guarantee that we are implying or imposing the exact same treatment on every single insect. But we do know that we are imposing the exact same treatment on the containers that those insects are in. So the units are not the insects, but the 20 containers that contain the same number of insects. That one was a pretty commonly missed one. I think a lot of folks said it was the insects. So what is the response variable? What is the outcome of this experiment? It is the number of insects that are still alive in each container 1 week after spraying. All right, so part 2, does the experiment have a control group, and explain your answer? The answer is yes. My explanation is that there is a dosage level, or there is a fungus mixture of 0 milliliters. So this is the control group, the container that receives no fungus at all. That's as pretty straightforward that it needs to be. So you need to state that there is a control group and then explain which group is the control group. So it's the one that has 0 milliliters, or the one that doesn't get any fungus. All right, Question 3, describe how the treatments can be randomly assigned to the experimental units so that each treatment has the same number of units. Step 1, assign each of the containers a number from 1 to 20. Write those numbers on a slip of paper. Put those slips of paper into a hat and mix it thoroughly. Pull out, without replacement, a slip of paper. The first 5 slips of paper will go to the control group. The next 5 will go to the 1.5 milliliter per liter. The next 5 will go to the 2.5 milliliter per liter, and the last 5 will go to the 3.75 milliliter per liter. So, I mean, that's pretty straightforward. Since there's 20 of them, I'll put them in groups of 5 because there's 4 treatment groups. So if you have any questions, please email me you can send a comment on this. You can also email me as well. A few notes on question C. When you use the slips of paper thing, you don't have to state that it's without replacing. It is implied with slips of paper. So keep that in mind. You could also use a random number generator and talk about that. I would suggest the slips of paper thing, especially for random assignment, is the most efficient way to go. Well, here's something that's kind of interesting. If the response states that insects are the experimental units, so if you said insects were the experimental units, the response in part C can be in terms of insects in the containers. In either case, the 3 components are used to determine the score. So yeah, like if you identified the units as the insects and then kept that concept for part C, they aren't going to mark you down again. So that's an example of a question where, just keep going with your answer. I think that's it. I think that's all. Those are all the comments that I have. Slips of paper, good to go. You can use the slips of paper thing for even crazier examples as well. It's a very efficient way to randomly assign. Yeah, I think that's all I got to say about that one. So I tossed in a probability question as well, a little two-way table action going on here. So we have question 3. A medical researcher surveyed a large group of men and women about whether they take medicine as prescribed. The responses were categorized as never, sometimes, or always. The relative frequency of each category is shown in the table. So they're showing us in terms of probability. One person from those surveyed will be randomly selected. What is the probability that the person selected will be someone whose response is never and who is a woman? So that is never and who is a woman. So this is the probability right here. So the answer for this one, we're looking for the probability of never and woman. That is 0.0636. Okay, this is and. So yeah, that's so and statements are the intersection of the two. What is the probability that a person selected will be someone whose response is never or who is a woman? So the response is never or they're a woman. So the response is never. So, I could randomly choose a male that has never taken their prescription, and that counts, right? Because it's never or who is a woman. So if it's a male who never takes their prescription, that's going to count in this case. Or who is a woman. So if I choose a woman who always takes their medication, then it still counts. Now, if I choose a randomly selected woman who never takes their prescription and is also a woman, then that satisfies both, so we're still satisfied. So what I like to do with or statements is it's the probability of never, so it's all of this, or the probability that we select a woman. So all of this. Okay. And I'm looking at the totals. So the probability of never selecting, or the probability of selecting somebody who never takes their prescription is right here, 12%, right? Combined with the male and the female, 12% of the people in this study never take their prescriptions, or say they never take them. Then the probability I randomly choose a woman in this is 53%. Now, this is what we're doing here. We got probability of never or woman. This is the union, this is the or statement. So or statements, we can add them together. So we're going to take the probability of never was 12%, plus the probability of choosing a woman, which is 53%. However, this is incorrect if you just simply add them together. Now, you've seen in separate cases in other videos that we have added probabilities. Well, if they are mutually exclusive events, we can simply add probabilities together and not have to worry about a thing. However, these are not mutually exclusive because they can happen at the same time. Notice when I add, or when I consider this 12%, I'm including women who never take their prescription. And when I add this 53%, I'm considering that same percentage. So I double counted the 6.36%. So I have to subtract the 6.36%. So we'd get, so make sure that you subtract, if there is one, for an or statement. Okay, part 3 of question 1. What is the probability that the person selected will be someone whose response is never, given that the person is a woman? So we know the person's a woman. So we have just found a 53% probability of something happening. So the 53% has happened. So 6.36% is what percent of 53%? So now we have the probability of never, given that the person is a woman. So this probability calculation is strictly out of the probability that the given occurred. I'm going to say this, the probability of N and W. There is a formula in your formula sheet. So this probability is out of the given. So essentially, what percent is 6 out of 53? In other words, because the 53% has already happened. It's out of the probability that we've chosen a woman, which is 53%. So that's the thing that has happened. So the probability that they never take the prescription and they're a woman, it's about a 6.36% chance. So what is 6 out of 53? In other words, it's a little bit over 10%, 12%. Next question. For the people surveyed, are the events of being a person whose response is never and being a woman independent? Ooh, independent? Well, here's something that a lot of folks kind of mistake a little bit. Are the events never take the prescription in woman, are they mutually exclusive? The answer to that is no, because they can happen at the same time in this survey. Are they independent? Does knowing one of the events influence the probability of the next event occurring? So I'm going to do this. Well, what's the probability that I just choose somebody from this survey and they never take their prescription? Well, if I consult my two-way table here, the probability that I choose somebody who never takes their prescription in general is 12%. Watch this. Let's say, so this is the probability I choose somebody who never takes their prescription. Let's say that then I know the person's a woman. Now what's the probability that they never take their prescription? Well, we actually just did this calculation and it is also 12%. So did knowing the person is a woman change the odds, change the probability that the person never takes their prescription? And the answer is no. That didn't matter, which is exactly the definition of independence. Knowing the person was a woman in this study does not change the probability that they never take their prescription. So the answer is yes, these are independent events for this study, because knowing the person is a woman does not change the probability that the person never takes their prescription. Assume that in a large population, the probability that a person will always take medicine as prescribed is 54%. If 5 people are randomly selected from the population, what is the probability that at least 4 people will always take medicine as prescribed? Show your answer. I'm going to say X is the number of people who always take their prescription out of a random sample of 5 people. So essentially what I'm doing is this. What's the probability that X is at least 4? Well, let's check this smells like a bin. This smells like a binary random variable. So B, is it binary? Yeah, they either take their medication or they don't. I, is it independent? Yes, because it's a large population and we aren't taking more than 10% of the population. Is there a certain number of trials? Yes, we're taking 5 people out of the population. Is it the same probability of success? And they give that, they say the probability the person will always take their medicine is 54%. So we're going to assume that that's the same regardless, and also with the 10% condition being involved, we're going to be okay with the success. So this is a binary random variable. So if I'm saying what's the probability that it's at least 4, well, that's the probability of being 4. Or, notice how I'm adding here, the probability that it's equal to 5. So the probability that 4 out of 5 people take their prescription, or that all 5 of them do. I'm going to start with the 5 of them first. I like to think about it as little slots, and this is saying that all 5 people always take their prescription. Well, they told us that it's a probability of 0.54, so this is the scenario. Are there any other ways that this could happen? No, this is the only way that all 5 people would take their prescription always. Also, for a binomial random variable, we have this formula here that's going to be really helpful. With the 5 out of 5 case, it's pretty straightforward. But what it would look like, I mean, obviously it's, 0.54 to the 5th, and I'm going to say times its complement. This really doesn't matter, but it's nice to see. 0.46 to the 0, because it doesn't happen at all. And then the number of ways that this occurs is 5, choose 5. Okay, so I'm going to write it like this is my binary setup, but really, it's just going to be this number here, because this becomes 1. Turns out this becomes 1 as well. Now let's take a look at probably that it's 4. Well, that could be 0.54 times 0.54 times 0.54 times 0.54, and then we get somebody who doesn't always take their medication. So right? So this is one way to get 4 successes out of 5. Or you could have, the first person not always do it. Or, so a few things to consider. Every single one of these has 4 successes and 1 failure. The successes are the 54% and the failure is 46%. Now the total number of arrangements that this could happen is 5, choose 4. And so this is equal to the probability that x equals 4. And we can find each of these by going to our calculator, which is 0.19554, 557, plus 0.04592, 0.24149. 0.24149. Whew! So that's the probability of at least 4 people in your sample of 5 who always take their prescription. So it's either 4 out of 5 or it's 5 out of 5 people. We are now going to be going over our first question 6. This is called an investigative task. They're going to introduce us to maybe a crazy concept, new concept on the spot, and it is expected of us that we can apply our skills that we've learned in AP Stats and our critical thinking skills that we've developed over our high school career. Yeah, this is known as the bootstrap problem. Emma is moving to a large city and is investigating typical monthly rental prices of available 1-bedroom apartments. She obtained a random sample of rental prices for 51 bedroom apartments taken from a website where people voluntarily list available apartments. Describe the population for which it is appropriate for Emma to generalize the results from her sample. The distribution of 50 rental prices of the available apartments is shown. Okay, so describe the population for which it's appropriate to generalize the results. Well, a few things to consider. She got it from a website where people voluntarily list available apartments. So, because random sampling was used, the results of the sample may be generalized to the population of rental prices for 1-bedroom apartments in the city that are listed on this particular website at the time the sample was taken. So be really cautious of a few things. It was a random sample, so you can generalize to a population. That's going to be a big word. However, the population that you can generalize it to is people who would post their apartments on this website at this time. So be really kind of picky about that population, but you can generalize it to a population because it was a random sample. If it wasn't a random sample, then you couldn't generalize it to a population. So make sure that you kind of justify there that you are generalizing to a population because of random sampling. Emma wants to estimate the typical rental price of a 1-bedroom apartment in the city based on the distribution shown. What is a disadvantage of using the mean rather than the median as an estimate of the typical rental price? Okay, so pretty clear here. It is skew right. Mean is a measurement of value. So this tail here will influence the mean. So the mean is going to be an overestimate of the typical rental price. because of this right tail. So the mean is going to be influenced by the tail here and these potential outliers because it's a measurement of value. The median is the best or the better of the two because it's a measure of position, and so it's going to be significantly less influenced by the tail and these potential outliers out here. So to answer the question, what is the disadvantage for using the mean rather than the median? Well, the mean will be an overestimate of the typical rental price, and the median will be better suited because it's not going to be as influenced by the outliers and the right skew. All right, part C. Emma is not satisfied with just using a sample median. Emma wants a range of values. Instead of using the sample median as a point estimate for the population median, Emma wants to use an interval estimate. However, computing an interval estimate requires knowing the sampling distribution of the sample median for samples of size 50. Emma has 1 point, her sample median, in that sampling distribution. So if we were to take the median here, that would be her 1 point. That would be her sample median. Using information about rental prices that are available on the website, describe how someone could develop a theoretical sampling distribution of the sample median for sample sizes of 50. So that word theoretical is really, really important. So theoretically, to determine the sampling distribution of median rental prices for random samples of 50 one-bedroom apartments from this population, Emma would need to obtain every possible sample of 50 one-bedroom apartments from the website and compute the median of each of those samples. The collection of all possible sample medians is the theoretical sampling distribution for sample medians. So you'd have to take every single possible sample of size 50 from the population, calculate the sample median, and then plot all those values to get the actual sampling distribution. All right, so think about it like this, right? This is our population of rent prices. Maybe it would look more, I don't know, like this. So population of rent prices. And you got some real high end. So let's say for median. Now I can't go to 50. However, this is just a nice little reminder. So what Emma would have to do is take every single possible sample of size 50 and then find the sample median of that. So you're going to see a pink ploop right here. This is the median of this sample of size 50. You could imagine if it was 50 instead. And then what she would have to do is do it again. Now this is a simulation. This is not performing the theoretical. What you'd have to do is get every single possible sample of size 50 and then plot the median. Let's do it again. So she would have to do every single possible sample of size 50, plot the median, the sample median. So far I've created 3 sample medians out of 3 samples of size. Well, in this case it's 25, but you can imagine if it was 50. And you'd have to do this for every single possible one. This is not the best example because this is not going to be every single possible one. I could repeat, but this would be creating an approximate theoretical sampling distribution. In your response, you'd have to explicitly say that you'd have to get every single possible sample of size 50 and then plot the sample median to get the true sampling distribution of medians for this population. Emma, really nice work here. Because Emma does not have the resources to develop a theoretical sampling distribution, she estimates the sampling distribution of the sample median using a process called bootstrapping. In the bootstrapping process, a computer program performs the following steps. Take a random sample with replacement of size 50 from the original sample, calculate and record the median of the sample, repeat the process to obtain a total of 15,000 medians, which is essentially what you just saw in the animation. Then they give you this big old table, and it looks really intimidating because it's not a graph. So what this is Emma ran a bootstrap process. This is 15,000 medians on a table. So to kind of justify or kind of explain, it'd be like, if I were to plot this, right? This is a median of 2,345. That happened one time in this process. In this simulation, think of the pooping block simulation that you just saw. A median of 2,390 happened 13 times out of 15,000. So this is showing you all the sample medians, or the median hats, right? This is showing you how often a sample median occurred. And it may look, something like this, but instead, like the way that this will be adjusted, it would say like sample median rental price and then how often it appeared. So I know a few things. I know the frequency of all these medians will add up to 15,000 because that's how many there are. Okay. The bootstrap distribution provides an approximation of a sampling distribution of the sample median. A confidence interval for the median can be constructed using a percentage of the values in the middle of the bootstrap distribution. Use the frequency table to find the following: the 5th percentile and the 95th percentile. Right, so the 5th percentile is the median where 5% of the data, right, 5%, so I need to find 5% of 15,000, which is 750. The 95th percentile is 14,000. Okay. So the 5th percentile, so I need to find the median where 750 of the data is below, right? I want to try to find the median where 750 of the samples are below it. Same thing here. I want to try to find the median where 14,000 medians are below it. So I have to look, maybe I'll call the 5th percentile here, maybe I'll call it 0.05, and the 95th x 0.95. So I got to find this number. Well, the 5th percentile would be a cheap place, right? So the 5th percentile is 5% of the data is going to be below it. 5% of 15,000 is 750. So I kind of just have to count until I get up to 750. Oh, this is 14 so far. Add this, it's not enough. So 1 plus 13 plus 18. I'm kind of curious, like right here, obviously I know, so I'll stop here. I know that this, like if I go beyond 2,500, it's not going to be the 5th percentile because this is already over 750. So I could actually, as long as this doesn't add up to more than 750, which I don't think it will, we're going to be fine. Okay, yeah. So this adds up. This adds up to like 398. So what I'm going to do is I'm going to say that 2,500 is the 5th percentile. Because if I go beyond it, it's no longer, it's certainly not the 5th percentile. So I'm just going to say that 2,500 is the closest thing that I have to a 5th percentile for this approximate sampling distribution. So my 5th percentile is 2,500. And one thing, so my 95th percentile is the place where 14,000 medians are below it. I don't want to add all that up. That seems really not fun. However, what I can do, right, I could add this all up to try to get to 14,000, but I also know that 5% of 1,500, 5% of 1,500 is 750, right? And that's the lower bound. So if I, notice here, if I go 750 from 15,000, so maybe I could cut that 750 from the top is what I'm saying. I could cut the 750 from the top, and then I'll find the approximate 95th percentile as well, which is kind of helpful because I see here, if that's 700, right? So if I do 750 from the bottom, that's going to be our 5th percentile. 750 from the top will be our 95th because I know that if 750 is above it, 14,250 will be approximately below it. So if I look here, 2950 is at 700, which will certainly capture 750. Now, if I go to 2962.5, it's not going to capture at least 750 because this doesn't add up to 750, but this will certainly add to at least 750. So I'm going to say that this is our 95th percentile because if 5% is above it, 95% is below it. Okay. So I'm going to say that my 95th percentile is a median of 2950. Find the percentage of bootstrap medians in the table that are equal to or between the values found in part D. Well, I know these, I already added that up, just 398, so equal to or between. So I'm actually going to include this in our number here. So I'm going to say that these add 398 equal to or between. So I'm going to get everything that's on the outside. I'm going to add this up. So this is what I'm looking at here. Equal to or between is there's an equal to, there's an equal to, or everything between. So one option is I could add all of the frequencies, but that's a lot of adding. So what I'm going to do is I'm just going to add the outside of it, subtract that from 1500. The data that was between or equal to 2500 and 2950. So the number of medians between 2500, which is our 5th percentile, and our 95th percentile, the amount of data between that looks like to be 14,409. So there was 14,409 medians between these two positions. And out of a total of 15,000, about 96%. So what we've just done is we found that 96% of the data lies between a sample median of 2,500 and a sample median of 2,950. And then part F, use your values from part D and E to construct and interpret a confidence interval for the median rental price. Okay. Wow. So, I mean, the confidence interval, remember these are our confidence interval. This is a sample median. This is the one that we approximated to be the 5th percentile, and we approximated this one to be the 95th percentile. And actually gave us an approximate, remember, because we had to kind of do some rounding here, especially like right here and right here, it didn't add up exactly. But we did find that about 96% of the data, we created a 96% confidence interval for a sample median. So part F says, construct and interpret a confidence interval. We are approximately 96% confident that the median rental price of all one-bedroom apartments listed on this website for this city is between 2,500 and 2,950. So this was our first question 6. I really like this one because it made you create an approximate confidence interval for median, which is really neat. It used the idea of the pooping block example, used the concept of what a sampling distribution is to create a confidence interval for something we haven't made a confidence interval for. So if you have questions on this video, please put the comments in the Google Classroom. As well, you can email me. So my goal is that I'm going to be continuing to give you quizzes regarding previous AP stats examples and questions. So stay tuned, ask some questions. This has been Math Think. Miss you folks. Have a good rest of your day and your week. Yep, and then just go ahead and just try to toss stuff and hit it a few times.
Filming? Please catch it.